Electrolytic or ionic conductors which conduct the electricity through the migration of ions are called electrolytic or ionic conductors. 1 ohm centimeter equal to 100 ohm centimeter or 1 ohm centimeter equal to 0.01 ohm meter. If A equal to 1 m square and L equal to 1 meter, then kappa will be equal to G. Based on the magnitude of conductivity, materials are divided into conductors, insulators and semiconductors. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College Temple of Excellence. Today I am going to start session 3 from the chapter Electrochemistry. In the last class we have discussed about measurement of electrode potential and standard hydrogen electrode and also list of standard electrode potentials and importance of electrode potentials. So these are the contents which we have already discussed in the previous session. In the today's class, we will discuss about conductors, types of electrolytes, conductance of electrolytic solutions, measurement of the conductivity of ionic solutions, experimental determination of conductance of given electrolytic solutions. This is very important concept, as well as we can expect the numericals from this concept. Next, conductors, substance which allow the passage of electric current through them are called conductors. Means the substance which allow the electric current in them or through them will call conductors, and which do not allow the flow of electric current will call insulators. These are the two substances which will be related for electric current. And electrical conductors are two types, that is metallic or electronic conductors or non-metallic or ionic conductors. First we will see what are metallic or electronic conductors. Conductors which conduct electricity by the migration of electrons. By the migration of electrons where electricity will conduct, those substances or those conductors will call metallic or electronic conductors. Metals such as copper, silver, aluminium, etc. Non-metals like graphite and various alloys belong to this class. The electrical conductance in these materials is due to the presence of free electrons. Due to the presence of free electrons, these electronic conductors will passage the electric current. The passage of electric current through these materials causes only physical changes in the materials. Due to this passage of electric current in the materials, physical changes can be seen, just the physical changes. Next, factors affecting the metallic conductance. What are the factors? The nature and structure of the conductors, the number of valence electrons per atom, temperature, the applied potential difference. These are the 4 factors which affect the metallic conductors. Nature and structure of conductors, the number of valence electrons per atom. Next, temperature conductance decreases with the increase in temperature. When the temperature is increases, the flow of current in the substance or through the substance will decrease. The applied potential difference. Next, electrolytic or ionic conductors. Okay, the conductors which conduct electricity due to the migration of ions. Due to the migration of ions, those electrodes conduct the electricity through migration of electrons, that is electronic conductors. This is electrolytic or ionic conductors which conduct the electricity through the migration of ions are called electrolytic or ionic conductors. Substance which conduct electricity either in solution state or in fused state. It will conduct electricity either in solution state or in fused state are known as electrolytes. Okay. Thus all electrolytes are electrolytic or ionic conductors. Whichever the conductors which will conduct the electricity in a solution state or in fused state, those will called electrolytes. All the electronic or ionic conductors will be considered as electrolytes. The passage of electricity through ionic conductors causes chemical decomposition of the substances. In the electronic conductors or metallic conductors, there you can expect only the causes of physical changes in the substance, but here chemical decomposition of the substance you can observe due to the redox reaction. Example, electrolytic conductors are aqueous solutions and fused states of acids, bases and salts. Here, due to the redox reaction, you can see the chemical decomposition over the substances. Next, factors affecting the ionic conductance, nature and concentration of electrolytic conductors, size of the ions produced and their solvation, the nature of the solvent and its viscosity, and temperature. When the temperature is getting increased, here conductance is also getting increased in ionic conductors. Next, types of electrolytes. There are two kinds of electrolytes, that is strong electrolytes and weak electrolytes. First we will see strong electrolytes. The electrolytes that ionize almost completely in aqueous solutions at moderate concentrations are called strong electrolytes. That ionize almost completely we call strong electrolytes, that is sodium chloride, potassium chloride, etc. And weak electrolytes, the electrolytes that ionize partially in aqueous solution at moderate concentration. Means if it ionizes completely in the aqueous solution, that is strong electrolyte. If it is ionized partially or incompletely, we will call it as weak electrolyte. For example, acetic acid, benzoic acid, carbonic acid and hydrofluoride and etc. There are substances called non-electrolytes also. Substances which do not ionize both in aqueous solution and fused state and therefore do not conduct electricity are known as non-electrolyte. It will not form or it will not ionize both in aqueous solution or in fused state and they do not conduct electricity, we will call it as non-electrolytes. Those are all covalent compounds like urea, benzene, sugar, ethanol, chloroform, ether, etc. Once again, there are two kinds of electrolytes, that is strong electrolytes and weak electrolytes. Strong electrolytes are, they will ionize completely in aqueous solution at moderate concentration. Example, sodium chloride, potassium chloride, etc. Weak electrolyte, the substance which will ionize partially or incompletely at moderate concentration in aqueous solution, we will call it as weak electrolytes. Example, acetic acid and benzoic acid, etc. And there is another category called non-electrolytes which do not ionize in aqueous solution or in fused state and it will not conduct electricity. Also, those will call it as non-electrolyte. Example, covalent compounds like urea, benzene, ethanol, etc. Next, conductance of electrolytic solutions. First, we will see resistance. Resistance is a measure of hindrance for the flow of electricity in the conductors. In the conductors only, the flow of current will not flow in the very easily. There is some hindrance. That hindrance of flow of current, we will call it as resistance and it will be measured in ohm. This is the symbol. According to Ohm's law, the resistance offered by a substance is directly proportional to the length and inversely proportional to its area of cross section. In case of electrolytic solution, L represents the distance between two electrodes and A is the cross sectional area in the electrolytic solution. Once again, resistance is the hindrance of flow of current in the conductors. It will be measured by ohm. According to Ohm's law, resistance is directly proportional to the length and inversely proportional to the area of cross section. In the electrolytic solution, this length represents the distance between the two electrodes. If it is two electrodes are present parallelly or inserted parallelly in the solution, that distance will be calculated as L and area of cross section of each electrodes will call it as A. Okay. Whenever the proportionality has been introduced, there proportionality constant should be there. So, R equal to rho into L by A. Rho is the proportionality constant and is known as specific resistance or resistivity. This is rho. This will be called it as proportional constant and also it is known as specific resistivity or specific resistance. So, A equal to 1m square and L equal to 1m. Then R equal to rho. Okay. So, the resistivity for a substance is defined as the resistance of a substance whose length is 1 meter and area of cross section is 1m square. Its unit can be derived as follows. Rho equal to R into A by L, that is resistance into area of cross section by length equal to ohm into meter square by meter, ohm into meter. Thus, the SI units of resistivity are ohm meter, but CGS unit ohm centimeter. It is also used and 1 ohm centimeter equal to 100 ohm centimeter or 1 ohm centimeter equal to 0.01 ohm meter. This is about resistance and resistivity. Next is cell constant. Cell constant will be represented by G star. The ratio of the distance between the two electrodes, that is L to the area of cross section of the electrodes, is known as cell constant. L by A means in the electrolytic solution, as I told, the distance between two electrodes by area of cross section of the electrodes. Here L by A only, will call it as cell constant, will be represented by G star. Next is conductance, will be represented by G. Conductance is the measure of ease with which electric current flows through the substance. Here no hindrance of electric flow in the substance or conductors, will call it as conductance. Therefore, it is the reciprocal of resistance. It is the opposite of resistance. The SI unit of conductance is Simon, represented by the symbol S, and it is equal to ohm or per meter. Okay, this is reciprocal, right? So conductance will be equivalent to 1 by R, that is resistance. Next, conductivity. Conductivity will be represented by kappa, that is a Greek word. The reciprocal of resistivity is called conductivity or specific conductance. It is represented by the symbol K, that will be termed as kappa. So when R equal to rho, this is R equal to rho. So this is reciprocal of resistivity. So kappa will be reciprocal of rho. The SI units of conductivity are Simon per meter. It can also be expressed as Simon per centimeter. 1 Simon per centimeter equal to 100 Simon per meter. But rho equal to R into A by L. Kappa equal to 1 by R into L by A equal to G into L by A. These terms you know, G is conductance, L is length, A is area of cross section. If A equal to 1 m square and L equal to 1 meter, then kappa will be equal to G. Conductivity of a material in Simon per meter is defined as the conductance when the length of the conducting material is 1 meter and area of cross section will be 1 meter square. Or the conductivity of a solution at any given concentration is defined as the conductance of the solution contained between two platinum electrodes of unit area of cross section and kept apart by a distance called unit length. Here also the distance between two platinum electrodes also you can consider as length. That area of cross section of electrode will be A. You can term as conductivity like that also, or else length of the conductor will also termed as L or area of cross section. Next, the conductivity values of some materials at 298.15 Kelvin. For sodium 2.1 into 10 to the power of 3, copper 5.9, silver 6.2 into 10 to the power of 3, gold 4.5 into 10 to the power of 3, iron 1.0 into 10 to the power of 3, graphite 1.2. Insulators like glass and Teflon 1.0 into 10 to the power of minus 16, Teflon also same but 10 to the power of minus 18. In the aqueous solution, pure water 3.5, 0.1 molar HCl that is 3.91, 0.1 molar KCl 0.14, 0.1 molar NaCl 0.12, 0.1 molar acetic acid 0.047, 0.01 molar potassium chloride is 0.016. Semiconductors, if it is copper oxide is 1 into 10 to the power of minus 7, silicon is 1.5 into 10 to the power of minus 2, germanium is 2.0. These are the sum of the conductivity values at the temperature 298 Kelvin. Okay. From the table, it is clear that the conductivity depends on the nature of the conductor, and also conductivity increases with increase in concentration. When the concentration of the electrolytic solution will increase, conductivity will also increase, since the number of ions per unit area will also increases. Conductivity depends on the temperature and pressure at which measurements are made. Materials are classified into conductors, insulators and semiconductors depending on the magnitude of their conductivity. Based on the magnitude of conductivity, materials are divided into conductors, insulators and semiconductors. Next, measurement of the conductivity of ionic solutions. Conductivity of ionic solutions can be determined by Wheatstone bridge. The direct measurement of resistance of electrolytic solution by using Wheatstone bridge is not possible because of the following two reasons. Usually, conductivity of ionic solution can be measured by Wheatstone bridge, but resistance of the substance or a resistance of electrolytic solution will not be directly measured by Wheatstone bridge because of two reasons. Those two reasons are direct current cannot be passed for it, the temperature will change or the composition will change in the electrolysis. Solutions cannot be connected to the bridge like other solid conductor. Okay, these are the two reasons. The first problem is solved by passing alternating current. Here they have given direct current cannot be used, but by the usage of alternating current we can use. The second problem is solved by using specially designed cell named called conductivity cell. They have told solutions cannot be connected to the bridge, so they have used conductivity cell. Two simple designs of conductivity cell are shown in below. Okay, these are the conductivity cells. Next, measurement of the conductivity of ionic solution. Conductivity cell consists of two platinum electrodes coated with platinum black. Here, conductivity cell will be consist of two platinum electrodes coated with platinum black. These two electrodes have area of cross section equal to A and are separated by distance called L. The solution is placed between these two electrodes of length and area of cross section A. The resistance of this electrolytic solution is given by R equal to rho into L by A. R equal to L by kappa into L by A. Okay. The ratio of L by A is called cell constant. Thus, the cell constant is defined as the ratio of the distance between the electrodes to the area of cross section of the electrodes. The cell constant is usually determined by the measuring the resistance of the cell containing a solution whose conductivity is already known. Cell constant we know that is area of length or distance between two electrodes by area of cross section, right? So, if we know the cell constant, the next by knowing conductivity of one cell we can measure another thing. Here G star equal to R into kappa. Next, the experimental determination. The determination involves the following two steps. First step, determination of cell constant of conductivity cell. In the theoretical version what they told, you have to first determine the cell constant of conductivity cell. So that is the first step. Conductivity cell of suitable design is filled with KCl solution, that is potassium chloride solution of known conductance. Okay, conductivity cell will be suitable with design of potassium chloride solution of known conductance. It is connected to Wheatstone bridge as shown in the figure. Okay, here conductivity cell will be connected. This is resistance 1, 2, 3 and 4. R1 is a variable resistance. R2 be the resistance of conductivity cell. R3 and R4 are the fixed resistance. These are the fixed resistance and this is variable resistance. This is conductivity cell. P is the detector. The bridge is connected to an AC source of power as shown in figure. And also here we know direct current cannot be used. Here alternating current only should be used. Next, determination of conductance of the given electrolyte solution. Cell constant have been taken now by using Wheatstone. Now conductance of given electrolytic solution. The conductivity cell is now filled with given electrolyte solution. It is connected to the Wheatstone bridge similarly and the experiment is repeated. The resistance R1 of the electrolytic solution is determined. Conductance of the electrolytic solution is calculated using relation kappa equal to G star by R2. Okay. Now, you know the theoretical version of determination of cell constant or conductance, and by the experimental way also we have seen step 1 determination of cell constant, step 2 determination of the conductivity of electrolytic solution. Okay. Now, molar conductivity. The molar conductivity of a solution at a given concentration and temperature is defined as the conductance due to all ions produced from 1 mole of an electrolyte dissolved. So, molar conductance will be equivalent to K into V. V is the volume in liter. containing 1 mole of the electrolyte. If C is the concentration of the solution in mole per liter, then molar conductivity equal to K by C or kappa by C. In the above equation, if kappa is expressed in Simon per meter and the concentration is mole per meter cube, then the units of molar conductivity are Simon meter square per mole. It may be noted that 1 mole equal to 1000 into molarity, and hence kappa into Simon per meter 1000 by molarity. M is nothing but molarity of the electrolytic solution. Molar conductivity is nothing but the conductivity of a solution at given concentration and temperature. As the conductance due to all the ions produced from 1 mole of an electrolyte dissolved. Okay. Next, equivalent conductivity. The conducting power of all the ions produced when 1 gram equivalent of an electrolyte is dissolved in volume ml of solution. Okay. That was how much electrolyte was dissolved. 1 gram equivalent will be dissolved. K into 1000 by N. That was molarity, and this is about normality. Ohm per meter per centimeter or mho into centimeter square. Next, variation of conductivity and molar conductivity with concentration. Now you have seen molar conductivity also, and that molar conductivity with concentration, how it will be varied, we'll see now. Both conductivity and molar conductivity change with the concentration of the electrolyte. This one we know, it will be dependent on concentration of electrolyte. With the increase in dilution, conductivity decreases. When the concentration decreases or dilution increases, conductivity will also decrease because number of ions will be less. This is because the conductivity of the electrolytic solution depends on the number of ions in a unit volume. Dilution means what? The ions will be decreased, so conductivity will also decrease. With the increase in dilution, the number of ions per unit volume decreases and conductivity will decrease. Molar conductivity of the electrolytic solution increases with dilution. Okay. Normal conductivity will decrease as I told, but molar conductivity of electrolyte will increase. In case of strong electrolyte, interionic interactions decreases with the increase in dilution, which increases the molar conductivity. In case of strong electrolyte, what will happen? Interionic interactions will decrease because of dilution will increase. In case of weak electrolyte, the degree of dissociation increases with increase in dilution. Hence, total number of ions in the solution that contains 1 mole, the electrolyte dissolved increases. Therefore, molar conductivity increases. In strong electrolyte, molar conductivity will increase with decrease in dilution, but in weak electrolyte, it will be vice versa because of interionic interactions. Now, we'll see variation of molar conductivity in strong electrolytes. For strong electrolytes, there is no increase in the number of ions with dilution because strong electrolytes are completely ionized in solution at all concentration. With respect to strong electrolytes, there is no dilution further. However, in the concentrated solution of strong electrolytes, there are strong forces of attraction between the ions of opposite charges called interionic forces. As I told, here interionic forces will be more. So, concentrated solution of strong electrolytes, they will show strong force attraction between the ions. Due to these interionic forces, the conducting ability of the ions is less in concentrated solutions on dilution. Due to this interionic forces only, the conducting ability of the ions will become less. As a result, molar conductivity increases with dilution. Overall, by this result, molar conductivity will increase with dilution. At infinite dilution, when concentration approaches to 0, resulting maximum molar conductivity, we will call it as limiting molar conductivity. When the infinite dilution will be there, the concentration approaches to 0. Okay, here everything will be fixed and that will be called it as limiting molar conductivity. The conductivity of electrolytic solution at infinite dilution is called limiting molar conductivity. The molar conductivity of strong electrolytes decreases with increase in concentration or increases with dilution. The variation in molar conductance with concentration can be studied by d by Huckel-Onsager equation. Okay, molar conductivity equal to limiting molar conductivity minus AC to the power half. This is molar conductivity at given concentration, and this is the molar conductivity at infinite dilution. A is constant and C is concentration of electrolytic solution. This is the d by Huckel-Onsager equation. See, this is the graph. Molar conductivity versus concentration. Next, variation of molar conductivity with respect to weak electrolytes. Here everything will be opposite of strong electrolyte. For weak electrolytes, the variation of molar conductivity with dilution can be explained on the basis of number of ions in solution. Here number of ions in the solution is very much important, so it will be explained through that. The number of ions furnished by an electrolyte in solution depends upon the degree of dissociation. Based on the degree of dissociation, the conductivity will be in weak electrolyte will be decided. With the increase in dilution, the degree of dissociation will increases, and hence number of ions in total volume of the solution will also increases. Due to the dissociation, the number of ions will get increased. Then as a result, molar conductance of weak electrolytes will also increase. Okay. Limiting molar conductance of weak electrolyte at infinite dilution cannot be obtained by extrapolation of molar conductivity to zero concentration. At infinite dilution, electrolyte dissociates completely. Here, like strong electrolyte, it will not be showing limiting molar conductivity, because in the limiting molar conductivity, the weak electrolyte will dissociate completely. But at such low concentration, the conductivity of a solution is so low that it cannot be measured accurately. Therefore, that limiting molar conductivity of a weak electrolyte are obtained by KOHLRASCH law of independent migration of ions. Here, what you have to understand means, in the strong electrolyte, interionic attractions will be more, and in this dissociation will be more in weak electrolyte. When dilution will keep on increases, dissociation of ions will also increases and conductivity will increases with respect to weak electrolytes. When the limiting molar conductance of weak electrolyte will reach, the dissociation of weak electrolyte will be completely done. So that small count at the low concentration of electrolyte or low concentration of solution, the molar conductivity will not be measured accurately. So that it will be obtained by KOHLRASCH law of independent migration of ions. KOHLRASCH law of independent migration of ions. The law states that limiting molar conductivity of an electrolyte can be represented as the sum of individual contributions of the anion and cation of the electrolyte. See, by the sum of contributions of cation and anion, the limiting molar conductivity will be estimated. For example, Na plus and Cl minus are limiting molar conductivity of the sodium and chloride ions respectively. So here it will be calculated. Applications of KOHLRASCH law. Using this law, degree of dissociation and dissociation constant of weak electrolytes of the type AB can be calculated. The degree of dissociation, that is alpha, at any concentrations will be given by alpha equal to molar conductivity by limiting molar conductivity. The dissociation constant K is given by concentration into molar conductivity square by limiting molar conductivity minus molar conductivity. Using this law, for both weak and strong electrolytes can be calculated from the values of molar conductivity of individual ions. Next problem. 1 molar solution of salt surrounding 2 platinum electrodes 2.1 cm apart and 4.2 cm square in area found to offer a resistance of 50 ohm. Calculate the conductivity of the solution. Given L equal to 2.1 cm, A equal to 4.2 cm square, R equal to 50 ohm. Then specific conductance kappa equal to L by A into 1 by R. So, K equal to 2.1 into 4.2 into 1 by 50 equal to 0.01 ohm per meter per centimeter. You have to represent it in Simon per centimeter. So, 0.01 Simon per centimeter. This equation is given by specific conductance. Due to that only, this is a very direct problem. And in the next class, electrolytic cells and electrolysis, quantitative aspects of electrolysis, Faraday's first law of electrolysis and second law of electrolysis, the factors that determines the product of electrolysis will be seen. I hope you have understood completely whatever I have taught today about conductors and its types. We'll meet in the next session. Thank you.